Okay, so in this um, lecture, we will try to understand the radioactive decay and the laws and the mathematics uh, pertaining to it. So, suppose if we have some sufficient numbers of radioactive nuclei, suppose these are some radioactive nuclei. Okay, so nuclei, this word nuclei, this is the plural form of the word nucleus. Nucleus is singular, and when we say nuclei, it means plural. So suppose we have this number of radioactive nuclei, and they are about to for some reasons they are about to decay or they will decay. So we have to just calculate their rate of decay. That is the number of decays per unit time. The rate of decay is the number of decays per unit time, and it is actually directly proportional to the number of nuclei. And when I say this mathematically, I mean this, that the rate of decay per unit time is directly proportional to the number of nuclei. Originally, what the number of nuclei was, this was the originally, let us suppose that at t is equal to 0, when it all started, this was the number of nuclei. The number of nuclei was n. So the rate of decay, and we can put a minus sign here. We can very conveniently put a negative sign because we are calculating decay. All right, we are calculating decay. That is, something is getting reduced. Something is getting reduced. Okay, its size, its mass, its quantity is going down. So we can put a minus sign. Okay, and now we can remove this proportionality sign and we can replace it by is equal to lambda n. Rearranging the terms, dn upon dt is equal to negative lambda n. The negative sign here connotes only one basic fact, that the number of nuclei, that is, this was originally the number of nuclei, it is disintegrating for some reasons, and because it's disintegrating, it's decaying, it's getting reduced. So something is getting reduced. This negative sign only denotes that its number is coming down, nothing else. And so lambda is this is decay constant. We can write it as, very conveniently, we can write it as decay constant. And now we will calculate the equation for radioactive decay, and we will separate the variables, that is, cross multiplying dn upon n is equal to minus lambda times dt, integrating it from n naught to n, dn upon n minus, from t is equal to 0 to t is equal to t time lambda dt. Here one thing which we have to note is the lower limit and the upper limit. The lower limit of time and the upper limit of time. Time cannot be negative. This is a very common sense thing. Time will be, if we start from now, then we will assume that the time is equal to 0 and whatever time limit we take. And originally the number of nuclei were n naught. Okay, we cannot take 0 because if there are 0 number of nuclei, then there will be no process, because you got to have some number of nuclei for a process to occur. So you need to have some number, some nuclei. Let us suppose this, the number of nuclei were n naught, and the final number after the decay, what was left to us, was n. All right. So we will now integrate it mathematically. This is very simple. This will be log to the base e capital N n is equal to minus lambda. Lambda will be taken out because it's a decay constant. It's a constant, so we can very well take it out of the integrating sign, and the integration of dt will be t. Integration of dn would be n. Sorry. Uh, this 1 upon n will be log to the base e capital N. All right, so we arrive at a result lambda t. Lower limit of time is from 0 till the upper limit is t, and this is the and now log n minus log n naught is equal to minus t minus 0. This will be log, we know log a minus log b is a upon b, log of a upon b. I hope you're through with the basic properties of a logarithm. So recall the change of exponential form to logarithmic form, that if we have a is equal to b raised to the power c, so this implies log to the base b a is equal to c, or we can write a is equal to b is equal to c. This can be converted, this logarithmic form can be converted to this exponential form, and this exponential form can be converted back to logarithmic form. So if we have this, we can convert it as n upon n naught is equal to e raised to the power minus lambda t. So we have just converted the logarithmic form into an exponential form, and we can convert back this exponential form into logarithmic form. All right, n upon n naught is equal to e raised to the power minus lambda t. So again, rearranging the terms, n is equal to n naught e raised to the power minus lambda t. So this is finally the equation for radioactive decay.